Okay, good evening, everybody, and welcome to another session of organic chemistry. In today's session, we are going to start our discussion on Chapter 5, which focuses on stereochemistry. Stereochemistry, of course, is the study of the three-dimensional nature of organic molecules. Okay, but before we start our discussion, let me make a few announcements. The your exam has been graded, and I will give them back to you at the end of today's lecture. And also, the homework assignment for this week has been assigned, and that is the end of Chapter 5 questions in OWL. And this is due on Sunday, October 6th at 11 p.m. Also, I have posted the exam number 2, which we are going to take, which is scheduled for October 22nd. So we want to begin to take advantage of this right away. Okay, now let's start this discussion on Chapter 5. Chapter 5, of course, gives you a lot of fundamental topics and concepts. As you can see here, we are going to discuss stereochemistry, which is the study of the three-dimensional nature or the study of the three-dimensional structures of organic molecules. Yes.
Which chapters were the exam?
Oh, okay, very good. Okay, the question is, which chapter are we going to cover in the next exam? To be chapters 5, 6, 7, and 8. So we do have a lot of material to cover. Okay, so in stereochemistry, we are going to discuss a variety of concepts and topics. We will look into different types of isomers. We discuss chirality and enantiomers, diastereomers. We will discuss Meso compounds, resolution of racemic mixtures, optical activity, and finally we shall discuss the impact of stereochemistry on organic chemical reactions. Of course, on this slide, we give you a list of outcome objectives. This list of outcome objectives you should use to guide your study of the content of this chapter. So I will advise that you come back to this list and check to see how much of the material you actually have mastered over the course of this week. Now the question is, what is stereochemistry? We say stereochemistry is the study of the three-dimensional structures of organic molecules. Or another way you can define stereochemistry, you could say it is the study of the spatial relationship of the atoms or groups of atoms in a molecule. In other words, we are going to look at the three-dimensional nature of organic molecules. And to do this, our focus will be on sp3 carbon that is attached to 4 different atoms or groups. Attached to 4 different atoms or groups. We are going to focus on the sp3 hybridized carbon atom that is attached to 4 different atoms or groups. And what do we mean by that? If you take a look at this molecule here, in this molecule here, all we are showing you is the 3-dimensional representation of those atoms or groups that are attached to this carbon right here. Okay? As you can see here, this group here is going away from us, and this chlorine is coming at you. Of course, the regular line bond, these are the bonds on the plane of the paper. Okay, so we are showing you here the 3-dimensional representation of those atoms or groups that are attached to this carbon here. And you can see here, since our focus is on that carbon, the rest of the molecule we do not represent using 3-dimensional structure. Now, if you take a look at this molecule also, look at this here, even though we have a 3-dimensional representation here, our focus will be on this carbon right here. Our focus will be on this carbon, because this is the only carbon in this molecule here that is attached to 4 different groups or 4 different atoms. Okay, some of you will wonder, why do we need to study stereochemistry? Okay, those of you in biology, those of you in pharmacy, of course in organic chemistry, those of you going to medical school, biochemistry, you will find that stereochemistry is almost at the centerpiece of most of what you will be doing. Because most bodily functions do rely on molecules that have specific stereochemistry. If you look at this here, glucose. Many of you know glucose, which is the source of energy for our body. The body only uses one stereoisomer. This is what we call D-glucose. The body does not use L-glucose for energy. If you look at your proteins, most of your proteins have only specific stereoisomers. So stereoisomers are very, very important, not only to the organic chemists, to a variety of other disciplines. Okay, so let us now look at the next slide. Okay, on this next slide, I've given you a schematic of the different types of isomers. You remember we started in chapters 3 and 4. We started with constitutional isomers. That is only one type of isomers. Now we are going to start our discussion on stereoisomers. As you can see, under stereoisomers, you have a whole variety of other types of stereoisomers. We have what we call diastereomers, enantiomers, and under diastereomers, we have what we call configurational diastereomers, and then cis-trans diastereomers. I believe we did a little bit of cis-trans diastereomers in chapter 4. Okay, so for now, most of you have already been exposed to constitutional isomers and cis-trans diastereomers. So at the end of this chapter, you should be able to take a molecule like this and use this to give an example of each one of these type of isomers. Okay, so let us start our discussion with enantiomers. The question that you guys want to know is, what are enantiomers? But before I give you the definition of enantiomers, let me give you some examples. Supposing we have this molecule here. Okay, supposing we have that molecule here. Remember we told you earlier that our focus would be on the carbon atom, the sp3 carbon atom, that is attached to 4 different groups or 4 different atoms. So let me go ahead and number this. 1, 2, 3, and 4. In this molecule here, which carbon atom is attached to 4 different atoms or groups? Anybody has an idea? Say 2. Okay, but that is correct. 2 is correct. If you look at this carbon here, carbon number 2, is attached to bromine. Also attached to chlorine. Okay, those are different atoms. Now, it's attached to carbon number 1. You say, well, it's attached to carbon here. It's also attached to carbon here. But now, this carbon is attached to 3 different hydrogen atoms. So we say this is a group right here. This group is different from this group. Okay? So we say all of this will be a group, and this is a group. So therefore, this carbon here, carbon number 2, is attached to 4 different atoms and or groups. In this case, bromine, chlorine, here methyl, and here ethyl. Now, because our focus is on the carbon that is attached to only 4 different atoms, we don't need to write this in 3-dimensional representation. Okay, so we could simply just do this, CH3. We could write the semi-condensed for those carbons that are not attached to 4 different atoms or groups. And this carbon here, carbon number 2, of course, we have bromine here. And carbon number 2 also have chlorine. And then carbon number 3, we have CH2. And carbon number 4, of course, CH3. You could do that. Our focus will be on this carbon. Now, if we want to write the 3-dimensional representation involving this carbon and the groups attached to it, well, what does it look like? You have that carbon. We have the methyl group. We have the ethyl group. And then, if we then do this, keep in mind, we told you earlier, groups the groups with the dotted line are going away from you. So this methyl, we said, is going away from you. This ethyl going away from you. And then we have the bromine here coming at you. And the chlorine right here. Both the chlorine and the bromine coming at you. What I've given you here is this structure. If you think of this, think of this as the bromine, the chlorine, think of this as the methyl, and think of this as the ethyl. Okay? This is what I've drawn for you. The chlorine and the bromine, they are coming straight at you. Okay? And of course, because this is a tetrahedral carbon, sp3 carbon, if you have 2 groups horizontally coming at you, the other 2 groups will be in the vertical position going away from you. You see that? Okay, that is the nature of a tetrahedron. Okay, so now we have this molecule here in a 3-dimensional structure. Supposing I now place a mirror here imagine that I place a mirror here. I want to draw the mirror image of this molecule here. Bromine will be there. Fluorine here. Methyl there. Methyl there. Okay, these two molecules here are mirror images. Now, if you try to superimpose this, you would not be able to superimpose them. Now, what do we mean by superimpose? If, for example, you just slide this molecule here to here, and you try to align all of the groups or atoms so they will coincide with each other, you cannot do it. And that is why I gave you this model here to look at. Okay? You cannot do it. So therefore, because we have mirror images that do not superimpose, we say these are different molecules. These are different compounds. And both of these molecules here, let us call this A. Let us call this B. Molecules A and B are enantiomers. Therefore, if I ask you what are enantiomers? Enantiomers are non-superimposable mirror images. Enantiomers are mirror images that do not superimpose on each other. I'll say non-superimposable mirror images. So they are stereoisomers, because the only difference between them is the orientation, the spatial orientation, the three-dimensional orientation of atoms within the molecule in space. That's all. That's the difference between them. They have the same molecular formula. They have the same attachment of atoms. The difference between them is the orientation of the groups or atoms. And they are mirror images that will not superimpose on each other. So we call them enantiomers. Okay? So that is the simple definition of enantiomers. Now, then you begin to wonder, if these are different molecules, what kind of name are we going to give them? Because if you look at this molecule here, does anybody know what the name of this molecule is? The way it is written right here. Based on your knowledge of nomenclature so far. Exactly. This will be 2-bromo, 2-chloro, butane. Fine. That is correct. Now, what if I tell you to name this molecule here? It's the same thing. So, but we are now telling you these are different compounds, so how do we name them? Okay, so we are going to get to the nomenclature shortly. Now, also now, if you take a look at this structure that I've given you here, this structure here, this structure here is a two-dimensional representation of this structure. Okay? This is a two-dimensional representation of this structure. Okay, this is three-dimensional representation. This is a two-dimensional representation. Now, what does this tell you? Actually, we do call this a Fisher projection. We call this a Fisher projection. This is very important, so listen very carefully. So we are going to be using this throughout this chapter. Now, what does this Fisher projection, what does it tell you? Keep in mind, this here, this Fisher projection here, is a representation of this molecule A. So therefore, in Fisher projection, so one, the horizontal groups are assumed to be coming at you. That is very important. When you write a Fisher projection, the horizontal group, you assume they are coming at you. Okay? Because this molecule here is a representation of this molecule here. Okay, so I would say horizontal bonds are coming at you. And then the vertical bond are going away, you assume they are going away from you. Okay? This is your Fisher projection. It's almost as though I've flattened this out, and then I've flattened this out. Okay, but in your mind, that two-dimensional representation, which we call Fisher projection, is actually a representation of a three-dimensional structure. So in the horizontal, at the vertical position, therefore, vertical bonds are going away from you. Keep this in mind, because this is very, very important. In a Fisher projection, in other words, if I write a Fisher projection, when you see the horizontal bond, you assume that they are coming at you. The vertical bonds, they are going away from you. Okay? Okay, so now we come back to how do we name molecules A and B. The reason I said the Fisher projection is very important because we are going to use the Fisher projection to name molecule A and B, and all the subsequent chemical molecules that we are going to name, we will use Fisher projection to do it. Okay? So what you will do in the future, you transform your three-dimensional structure into a Fisher projection. That is what we are going to be doing in the future. Okay, now, how do we name molecules A and B? To name molecules A and B, we use what we call the Kahn Ingold trilog. Kahn, C-A-H-N, Ingold Prelog priority sequence rules. And what does that mean? In the Can-Ingo Prelog priority sequence, what we start with, we are going to assign absolute configuration to the carbon that is attached to 4 different groups or atoms. By the way, let's tell you right away, this carbon here that is attached to 4 different groups or atoms, we refer to it as a chirality carbon. Okay. Sometimes we also call it a chiral carbon. Sometimes we call it a stereogenic center. In some books you might see stereogenic center. Now whatever you want to call it, chirality carbon, chiral carbon, stereogenic center, what it is, it must be a carbon atom or sometimes other atoms, but for our purpose, we are going to focus on carbon. It must be a carbon atom that is attached to 4 different groups or atoms. So if I ask you what's a chirality center, you should be able to say this is what it is, because it's very important. Okay. So in the Can-Ingo Prelog priority sequence rules, you assign absolute configuration to the chirality center. Assign absolute configuration to the chirality center. So I will call this chirality carbon, okay? And this absolute configuration we designate as R or S. R or S. We'll tell you what that means in a few minutes. And then you want to ask, what is absolute configuration? Absolute configuration is the specific 3-dimensional arrangement of the groups that are attached to a chirality carbon. Let me write it down. Absolute configuration is the specific 3-dimensional arrangement of groups or atoms attached to chirality center or carbon. Okay? So the absolute configuration is the specific 3-dimensional arrangement of groups or atoms that are attached to a chirality carbon. And we generally designate them as R or S. So then you say, where does the Can-Ingo Prelog priority sequence comes in? Where does it come in? To make the assignment, you take a look at the. Take this out. From now on, we are going to use the Fisher projection to make all of our assignments. To make the assignment, you take a look at the chirality carbon, and you assign priority. I do slightly different from your book. Your book says 1, 2, 3, 4. I use A, B, C, D. You have assigned priority from A to B to C to D to those groups or atoms attached to the chirality carbon based on atomic number. Okay? So therefore, we take a look at this carbon here. You see bromine. We say bromine is priority A. Okay, follow this now. And then what would be priority B? What is priority B? What is it? Chlorine, based on atomic number. So chlorine is B. Okay, let me get this out of here. Chlorine is B. Now, you then want to make a decision which is going to be C. If we take a look at this carbon, the ethyl or the methyl, which will be C? Ethyl. Why? You take a look at this carbon here. This carbon is bonded to this carbon. You also say, well, it's also bonded to this carbon. At that point, you cannot make a decision. Then you say, what is this carbon bonded to? This carbon is bonded to another carbon. But this carbon is only bonded to hydrogen. Therefore, this ethyl has priority. So therefore, we are going to make this C, priority C. And finally, this methyl becomes priority D. Okay? So, according to the can-INGO prelog priority sequence, we have already made the priority. Now we are going to make a motion. We are now going to make a motion from A to B to C, completely ignore group D, as if group D was in there. Okay? So we are going to make our motion from A to B to C. Completely ignore group D, as if group D was in there. Okay?
Priority is atomic number, not alphabetical, right?
Atomic number, yes. For the priority, you use atomic number, yes. Okay. So we make our motion. We go from A to B to C. Ignore group D. Now, if motion in this case, the motion is counterclockwise. If your motion is counterclockwise, then you say the absolute configuration of this carbon is S. You say the absolute configuration of this carbon is S. It's the absolute configuration of this carbon is S. So therefore, let us now name this compound, compound A. Okay? We determine that the absolute configuration of this carbon here is S. So how do we now name compound A? So we now say compound A to be S, paren, 2-bromo, then you name it as you normally name it, 2-bromo, 2-chloro, butane, and what do you think the name of the mirror image will be? What would be the name of the mirror image? Exactly, it would be R, paren, 2-bromo, 2-chloro-butane. Okay? So this is this name here. This name goes to this. R for this will become R, 2-bromo. You follow all of the rules that we taught you in chapter 3 and 4. Chloro, butane, these two enantiomers, therefore, they now have two different names. Okay. Now, each one of these enantiomers, we say it is a chiral molecule. This is a chiral molecule. This is also a chiral molecule. Chiral molecule in this case simply means that it will not superimpose on a spiral image. Okay. It is also, each one of these will also be what we call optically active. Any chiral molecule will be considered as optically active. This is also optically active. Okay, now, let us come back to this molecule here. We have this. Let me see which one. That is the S. The molecule that we call S, which is this one here, that is this one here. Let me see. So we have the chlorine coming at you. Is that right? To your right, yes. No. Yes, okay. This is the way you see it. Bromine on your right, chlorine on your left, methyl here, and this ethyl here. That is because you are looking at this molecule from here. Okay? Supposing, I want you to help me out here. Supposing, based on where you are looking, okay, get Miss Howard to also look here, right here, right? Just as you're looking, supposing you decide to look here. Supposing you decide to look here. In this case, you are looking here. This molecule hasn't changed. Okay? This molecule has not changed. Just looking right here. Now, what will be on your right? What will be on your right? In the Fisher projection. Chlorine. What will be on your left? Methyl. What will be on top of you? Bromine. And below you? Ethyl. It is the same molecule. Okay? Supposing, therefore, let me write that. Okay, give it to me. You have carbon here. What's on your right? What's on your right? Chlorine. Okay. Left, Methyl. Okay. On top, bromine. Below, ethyl. This is also a Fischer projection of the same molecule. Now, I could write this. Okay, another way we could look at it. Supposing we do this. Supposing we want to look at it here. Keep in mind, this molecule is not changing. You are the one changing your position. Supposing we want to look at it. Okay, give me the structure again. Give me the structure. Right is what? Ethyl.
Right.
To my right, right? Oh, I'm sorry. Sorry about that. I don't know my right from my left. Okay. Okay, my left. Okay, bromine. On top, methyl, very good. And below, I could write these two molecules here, A and B. And I say, tell me whether these two molecules are the same or enantiomers. Well, you know they are the same because the same molecule that we did. The only way you could tell whether they are the same or they are enantiomers is when you give the name, you assign absolute configuration. Okay? Okay, let us do that. Let's do absolute configuration. Okay? This is A, right? This is B. This is C. This is D. Now let us make our motion. I'm sorry, let us, yes, make our motion. A to B to C, ignore group D. Ignore group D. Now, according to this motion here, this is what kind of motion? Clockwise motion, right? Clockwise motion is R. There is a problem here. According to the IUPAC rule, when you make that motion, you are essentially assuming that the group of lowest priority is going away from you. That is the assumption. That's when we did the last one. The group of lowest priority was going away from us. That is the IUPAC rule. You are assuming the group of lowest priority must be going away from you. Now, let me ask you this. Which is the group of lowest priority here? Methyl. Is it going away from you or coming at you? It's coming at you. Okay, this is my rule. Add this to it. If when you make your motion, this is not in your book, but this is the rule that I made up, right? And I published this in 1982, long time ago, before most of you were born. If you make your motion, and the group of lowest priority is not going away from you, it's coming at you. Whatever motion you make, switch it. In other words, even though this is R, right? Then what you do, make a switch, because you are violating the rule. So actually this is supposed to be S, which is what we got before, the same molecule. So this is actually S. Okay, keep that in mind. You make your motion, because your book tells you something else, tell you to do this, move around, and forget all of that. Okay. If you use a Fischer projection, it's really very, very easy. Okay. Now let us do the same thing for molecule B. Okay. Let us do the same thing for molecule B. Keep in mind they are supposed to be the same molecule. Okay, even though they look different. Because in an exam, we could give you molecules that look different. You say, are they the same or are they different? The only way you can tell is to assign the absolute configuration, and then you name the molecule. If they are the same, then you say they are the same. If they are opposite, in this case, you say they are enantiomers. Okay, let us see. Let us assign. Let us look at B here. Okay, help me out here. Priority A, right? B, C, and D. So what do? We make our motion from A to B to C, ignore group D. A to B to C, ignore group D. What is that motion? Okay, motion is clockwise, which is S. Oh, no, sorry. A to B. Oh, did you get that right? Counterclockwise. Counterclockwise, which is S. Thank you. So it is S. Do we need to make a switch? No, because the group of lowest priority is already going away from you, which obeys the IUPAC rule guideline. Okay, which is what it's supposed to be.
So if it's on the top or the bottom, you can configure it as going away.
Yes, if it's vertical, you know that it's going away from you. If it's horizontal, according to Fisher projection, to Scominato. Okay? Which is S, and that's what it's supposed to do, because that we just made it from here anyway. Okay? Okay, very good. Okay, now we have given you what are enantiomers. What are enantiomers again? Anybody know what enantiomers are? Yes. Say that again. Exactly. Mirror images that do not superimpose on each other. In other words, non-superimposable mirror images. Those are enantiomers. Okay. Okay, so let us go to... Now, supposing we have this. Now, supposing we have this. From now on, I will be using Fisher projection formula, okay? Huh? No, it's just a different approach, that's all. Okay. You get to the same outcome, you know. Supposing we have this. So I've written this Fisher projection here. How many chirality centers do we have in this molecule? How many chirality carbons do we have in this molecule? Okay, let me number this. This is carbon 1, 2, 3, 4, and 5. How many? 2. We have 2 chirality centers here. Carbon 2 and carbon 3 are chirality centers. Do you see that? Because the requirement is for you to have a chirality carbon, that carbon must be attached to 4 different atoms or 4 different groups. If you focus on carbon number 2, you have a methyl group, right? Hydrogen, bromine, and then here consider this a group relative to carbon number 2. If you come to carbon number 3, focus on carbon number 3, we have ethyl group, bromine, hydrogen, and then this group here, consider this a group. Okay, so those are 4 different groups. Okay, so let us go ahead and assign absolute configuration to the chirality carbons here. Okay, anybody want to help me here?
Wait,
let us, yes.
You don't have to separate us into 2 different chirality carbons.
Yeah, but it's in the same molecule. It's in the same molecule.
You know what I'm saying? In order to name like the ABC, you don't have to break them off, like break the
Oh,
molecule in half.
oh no, no, you don't break anything. You just, okay, so that's what we want to do now. Take this out here. Let us name this. Keep in mind, even if you, for each chirality carbon you have in the molecule, when you want to assign the absolute configuration, you focus on one carbon at a time. That's what you do. Okay? Okay, let us do that. Let's focus on carbon number 2, this here. Priority will be, this is A, bromine, right? Now, what will be priority B? This group here will be priority B because this is attached to carbon and this carbon is attached to bromine. So therefore, this group here, now let me use a different color pen. This group, consider this a group, okay? And that will be B. Okay, what will be C? Metal. And D, hydrogen. Okay, now we want to make our motion. We make our motion from A to B. We go through B, ignore group D, as if D wasn't there at all. What is that motion? Motion is clockwise. Therefore, which is R. Therefore, take a look at this at the lowest priority group here. What is it doing? It's coming towards you. So what do we need to make a switch? Yeah, we make a switch. Therefore, it actually should be S. Yes.
Why wouldn't you make the bottom group the highest priority? Because it doesn't have the atom altogether.
Okay. Keep in mind. Okay, very good. Okay, relative to this carbon here, this carbon is directly attached to bromine, right? This carbon is also directly attached to carbon. So which has priority? Exactly. That's why we make bromine A.
Okay, so could you do it like naming, even naming in terms of the third carbon as well for the other carbon?
I don't follow that.
So right now we're doing like everything in terms of the second carbon.
Yes.
So could you also do it for the third carbon?
Oh yeah, that's what we're going to do. We're going to do that. We're going to do that. Yeah. See, that's what I told you. You may have several chirality carbon in the molecule, but you focusing on one carbon at a time. Okay? Very good question. Okay. So therefore, this is S. So the absolute configuration here is S. Now, we come back here and focus on carbon number 3. Okay? When we focus on carbon number 3, this will now be a group attached to carbon number 3. And this is another group, the ethyl group, and the bromine, and the hydrogen. So let us assign the priority. We have A. Where is B? On top, right? So this B, and the ethyl is C, and the hydrogen is B. Okay? So now what do we do now? We make our motion from A through B. We ignore group D as if it was in there to C. And what is that motion? The motion is counter, right? Clockwise, which is supposed to be S. Do we need to make a switch?
Yes.
Yes. because the group of lowest priority hydrogen is coming towards you. Okay, very good. I think you guys got the idea. So this should be R. So therefore this is R. So now let us give a name to this compound. What would be the complete name for this compound? What would be the complete name for this compound? Now we say 2S, parent, 2S, 3R. We have to, in this case, if you have more than one chirality center or carbon, you got to put a number by the absolute configuration. Okay? Then we continue with the rest of the nomenclature. This will now be 2, 3, dibromo, is that pentane? Okay, 2, 3 dibromopentane. Now, what if I ask you, what will be the name of the enantiomer of this molecule? What will be the name of the enantiomer of this molecule? Exactly. The name of the enantiomer will be 2R, because it has to be opposite. 3S, 2,3 dibromo, pentane, and that will be this molecule here. That will be the mirror image of this.
So in naming the enantiomer, you just switch the location of the chirality center.
Just a minute. Yes, in naming the enantiomers, the absolute configuration will just have to change. It will be the opposite. Okay? So this is the name for this, and this is the name for this here. Okay? Now, so we take molecule A and molecule B are enantiomers. Okay? What time do we have left? Okay. Okay. Now, in this particular instance, if you take a look at this molecule here, we say we have 2 chirality carbons. There is a formula that you can use to determine what is the maximum number of stereoisomers you could obtain from a molecule if you know the number of chirality carbons or centers. And that formula is 2 to the raised to the power of n, where n equals to number of chirality carbon. Huh? Oh, that will give you the maximum number of stereoisomers that you could obtain from this molecule. Okay, this is the maximum number. Maximum number of stereoisomers. From a molecule, if you know the number of chirality carbons. Okay, you use the formula 2 to the n. So based on that formula, what is the maximum number of stereoisomers obtainable from molecule A? 4, right? Very good, very good. Maximum number is 4. Okay? If maximum number is 4, got this? Okay. If maximum number is 4, let us see the, okay, of course, A and B are enantiomers, so those are 2. Let us see the other 2. Supposing I take this, bromine is here, hydrogen is here, and I switch the bromine to this other side, hydrogen is here, and then I draw the mirror image of this. Keep in mind, the mirror image of this is this one here. A and B are mirror images. Okay, so let us call this C and D. Okay? Okay, we say enantiomers A and B. Okay, what other enantiomers do we have here? Which one? C and D, exactly. C and D. Now, what is the relationship between A and C? What is the relationship between A and C? Say that again. Configuration. I thought you said it right. Configurational. Diastereomers. Now you want to know what are configurational diastereomers. Configurational diastereomers are stereoisomers that contain more than one chirality carbon and are not mirror images. Okay? Let me write that. I'll come back to this, okay? Configurational diastereomers are stereoisomers containing more than one chirality carbon, comma, and are not mirror images. Are not mirror images. Okay? So based on that definition, go back to here. Oh, you want me to go back? You want me to go back? Okay. Yes. Because they are not mirror images. Yeah. Yes. Yeah. They are completely different compounds. Okay. Okay. Configurational diastereomers are stereoisomers containing more than one chirality carbon and are not mirror images. Okay. So if we go back to here, Okay? What is the relationship between compounds, molecules A and C? They are configurational diastereomers, A and C. About B and C. B and C, they are not mirror images, even though they are stereoisomers. And each one of them contains more than one chirality carbon. So therefore, B and C are configurational diastereomers. About A and D. A and D. About B and D. Okay, so these are all configurational diastereomers. So this molecule, therefore, if I give you this molecule here, and I tell you to draw all of the possible stereoisomers for this molecule, and identify the relationship between them. You draw all the possibilities. Okay, since it contains only 2 chirality carbon, you know the maximum number of stereoisomers you will get is 4. And then once you draw them, you begin to now show us the relationship. Yes.
The name for C is also the same as the name for A. It's spelled the same, so would you be able to differentiate? Because C has the same name, so.
Say that again.
Well, I was thinking C has the same name because it's still 2 for the diagonal, but the configuration is different.
No, because the maximum you could get here is 4. Okay. Okay, anyway. So now we've given you enantiomers. We've also given you configurational diastereomers. How much time we left? One more thing before I let you. Oh, time. Okay. Now, supposing we have this. Supposing we have this. Just a minute. Supposing we have this molecule here. Yes, go ahead.
Is there any special way to name configurational diastereomers?
No, you just name, you assign the absolute configuration. Just the same way. Just the same way. Yeah. Okay. Supposing I give you this molecule here. How many chirality carbon does it have? 2. That is correct. That's 2. This here and this here, let us number them. 1, 2, 3, and 4. Carbons 2 and 3 are chirality centers. So therefore, you will expect, what is the maximum number of stereoisomers would you expect? 4, that is correct. But in reality, we only have 3. That is the maximum we are supposed to get. But in this case, in reality, we only have 3. I will show you why. Okay. 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 If we take a look at this, let us draw the mirror image. The mirror image will look like this. That is the mirror image. Let's call this A and molecule B. Can we superimpose those 2 molecules? Okay. Yes, you can. Okay. If you slide, right? You slide on top, right? And then you don't move it. The only requirement is you make it has to stay on the paper. Okay. You move it 180 degrees, right? When you have a Fisher projection. Okay, so if I simply move this, I hold my hand here, and then move this 180 degrees, what happens? I will get this. As long as it is a Fisher projection. The only thing you cannot do in a Fisher projection is to lift the structure of the paper, you cannot do that. Okay? As long as you don't do that, if all you do was just doing a 180-degree rotation on the paper, then you slide it. Molecules A and B are the same molecule. So therefore, another word for you to know, Meso. A Meso molecule or molecules are stereoisomers containing more than one chirality carbon comma, and will superimpose on their mirror images, and will superimpose on their mirror images. So molecules A and B, therefore, A and B are what we call Meso molecules. Okay? Now let us draw the other. In other words, A and B are the same. So let us draw the other isomers. Supposing we have this. Can we draw the mirror image of that? Okay, we call this C and we call this D. Okay? You find that C and D are enantiomers. Okay? What is the relationship between A and C? What is the relationship between A and C? What is it? Configurational diastereomer. Exactly. Very good. Okay, so we say configurational diastereomers A and C, A and D, B and C and B and D. Of course, we know that Meso is A and B, meaning that they are the same molecule. And that is why in this molecule here, the maximum number of stereoisomers you have is only 3, because A and B are essentially the same thing. Okay? Because, therefore, A and B will superimpose on their mirror images, we say Meso compounds are achiral. Meso compounds, we say they are achiral. Okay? Another way we also want to describe them is that they are optically inactive. Okay, so when we come back on Thursday, we will continue with this treatment of stereochemistry. And on Thursday, we are going to have a short 10-minute quiz on today's lecture, just on today's lecture. Short 10-minute quiz on today's lecture, on Thursday. Huh? Oh, ACAR, it will superimpose on its mirror image. Molecules that will superimpose on their mirror image. Yes. Yeah, the molecule as a whole. Now, I will also tell you one thing. For you to tell whether a molecule is a meso or not, generally they have what we call a plane of symmetry. If you look at here, you see what we call a plane of symmetry. Okay, you see the top and the bottom is almost like they are mirror images. When you see that, you know that molecule is a meso molecule. Okay. Okay, so I will give you back your exam.